Our next speaker is Nikita Zychowska. She is a member of our own Polish Astrobiology Society, and she'll talk about astrofitness, about musculoskeletal system and minds. So go ahead, Nikita.
Thank you. Can you hear me?
Yes, we can hear you all right. We can't see your screen.
Okay, now you see everything?
Yes, so go ahead and start your presentation.
Thank you. First of all, thank you everyone for coming here today. My name is Nikita and I will be talking about muscles, bones and human space, body in space, and about mice. My presentation is divided in 4 parts. The first part will be about space medicine. The second part will be about muscles and space atrophy muscles. The next part will be about rodent research, and the last part will be about bones and space osteoporosis. So let's go to the space medicine. What is it? It's a new field of science. Space medicine studies the impact of the space environment on the structure and physiology of humans. Space medicine can have such very answers, for example, how body behave in space, or why does it happen? Why do astronauts get osteoporosis or space atrophy in space? And the more important, how we can fight with that. So let's go to the part 2. And we have a mind map. Muscles, how do they work? The muscles was built in the myogenesis process. It's a very important process. And what is myoglobin? Myoglobin is a protein, and it contains iron and oxygen binding in this protein. It functions as an oxygen storage unit. It provides oxygen from our blood erythrocytes to the working muscles. And skeletal muscles are made up of the individual muscle fibers are divided into slow twitch and fast twitch. Slow twitch are very durable fibers, but their power isn't large. For example, slow twitch fibers have, for example, marathons, people who run in the marathon, and fast twitch. They are very quick energy consumer, but aren't countable of long work, but their power isn't large. For example, these are fast twitch. They have people who run to the, for example, short distance, like the 100 meters, for example. And now we know how muscles work, but now I wanna show you a very important process, the ubiquitin proteome system. In brief, oops, I did it again. It's essential protein of many cellular process. Ubiquitin is very small protein, and we can find that in our tissues of the people, animals, for example, and fish. It plays a very important role in protein generation and our other and other processes. Um, Proteins are modified by convalescent attachment to the small protein known as the ubiquitin. Um, and ubiquitin process serves as signal of protein turnover that leads to the rapid muscles of mass plaque. This process is carried out through an enzyme cascade, what we see in the picture, which includes three groups enzymes termed ubiquitin 1. Its activated enzyme, ubiquitin 2A2, is the injection enzyme, and ubiquitin A3 is a ligase. There are several ways of ubiquitin conjugation driving to ubiquitin process specific protein through ubiquitin proteolysis. And a lot of ubiquitin proteolysis system genes tended to be included in the skeletal muscle atrophy. These genes do their effect by modifying different processes aff- uh, which affect muscles mass, including myofibrillar protein degeneration. Uh, for example, myogenesis, inhibition, and even modulation of autophagy, as well as upstream regularity pathways. And we have atrophy muscles. Atrophy muscles we have in the arm, for example, when patient uh, not doesn't move a leg. For example, like a very long time, for example, this patient break this leg and uh, muscles are uh, small atrophy. And in this case, muscle atrophy is caused also by less use of muscles in space. The loss of skeletal muscles results in weakness, reduced mobility, and the tear, and um, and it's not good for our life and astronaut life. And how look like Astrofitness in the ISIS? The first three astronauts in the International Space Station have very restricted training. They have to exercise 2.5 hours per day. Uh, yeah, it's very, very big time. In the ICs, there is a treadmill, and when the astronaut had to exercise the treadmill, they have to wear a harness that keeps astronauts in the floor. And astronauts have to also a bike, but in the board ICs, this bike is without seat. Their feet are clipped on the pedals. And also in the ICs is the advanced resistance exercise device in brief ARID. It's a is perform high-intensity workouts. A machine make a resistance, and that's why astronaut can training lifting race. And we can go to the part 3 about rodent research. Okay, so what is the rodent research? To better understand the behavioral body of mammals in space, rodents are sent to the ICs to research. And there are so many missions on the ICs. For example, Rodent Research 1 was in the 2014. And what is going on? The complete rodent research experiment was about muscle atrophy in space. And this very important process, the ubiquitin proteome system, what I just said, plays a critical role in skeletal muscle atrophy. And muscle-specific ring finger 1, this ubiquitin ligase, increase with muscle atrophy in the arm. And in the rodent research 1, researchers assessed muscle changes to the hind limb muscles of mice exposed to the microgravity using 2 groups of mice. I'm sorry. The first group was divided to the muscle ring finger 1 gene believed to play the big role in triggering muscle wasting, and another group of white type mice was with normal expression of the muscle ring finger 1 gene. And after 21 days in the microgravity, the mice were exposed to the microgravity, and none of these genes shows in raised expressions. What does it mean? Does it mean that muscle atrophy in the microgravity is not similar in the air? And it's a big tip for us for another research. And we go to the part 4, to the bones. So bones were for example, we have a woman after menopause, and so many women in the north, for example, in the Poland, have osteoporosis. Bones also are lost in space. Under space conditions, bone resorption occurs after the new bone is formed. And for example, a very interesting fact is that the microgravity environment in space average astronaut lost average 1 to 2% of their bone mineral density every month. But, for example, women after menopause, and if they have osteoporosis, they lost the same percent, 1 to 2% of their bones, but every year. So, month and year is a big difference. And it's a big problem for example, when astronauts want to go fly to the Mars. Uh, yeah. And it's not only about bones. Ions of calcium go away from bone to the capilla, and from capilla to our kidneys. Um, there, there too much calcium in the kidneys can create kidney stones. It's a very painful sickness. The calcium balance, it's a difference between intake and ex. Uh,
You have 1 minute, Nikita.
Okay. It's a very big difference balance, and it's big. It's a bigger risk to the kidney stones. And how we can fight with that? We can make more exercise. We can enhance vitamin D3 and calcium. We can bring for hormone, for example, estrogen, progesterone, and bisphosphorante, for example. And yeah, thank you. That's it.
Okay, thank you, Nikita. Unfortunately, I can't see any questions in the chat box. I think I'll ask you a question on my own. How long does it take for astronauts to gain the muscle and bone mass after a mission on the ISS, for example?
When astronauts come back to Earth, have it depends. For example, when astronaut is older, their bones make slower, and for example, that can how long? For example, 2-3 years. It's a very long time.
Okay, thank you. I still can't see any questions on the chat box, so I think we'll move on to our invited speaker.